So let's use this formula. Okay, to evaluate these. Okay, so we're not using area, we're using the formulas that we learned in the last lesson. Okay, and I'm going to show you how we write this out. So just look at the don't worry about the 0 to pi, just look at sine. What's the antiderivative for sine? Negative cosine. So it's going to look like this. Negative cosine of x, I'm going to put it in brackets, evaluated from 0 to pi. So that's how we write it sometimes. You can also write it like this, with like a line.
Well, I like that one.
Okay. Sometimes it depends if I have multiple terms. I'll usually just put it all in brackets and then put the lower bound on the lower right, upper bound on the top right. Okay, so what are we going to do? So remember, this negative cosine, this is capital F of x.
So evaluate
Because
that
that's the antiderivative. So we want to evaluate this at pi
and minus.
and then subtract
Value that.
f of 0.
So we want to evaluate the integral where it was like initially evaluated?
Right, so we're going to
Integral
do...
in the first place.
We're going to do negative cosine of pi minus negative cosine of 0. So this is f of, capital F of pi minus capital F of 0. Do you see it? So now what's cosine of pi? Cosine of pi is negative 1, so if you have a negative in front, so it's negative negative 1. And then what happens here? What's cosine of pi?
Cosine of 0, you mean? First one.
I mean, cosine of 0
1.
is 1. So minus negative 1 means plus 1. So we get 2. So what we just did, so remember before I told you we didn't have a way to figure out the area under the sine curve? I gave you from 0 to 2 pi, and we found that just because the areas are going to cancel, we got 0. But now, we just basically proved the area under the sine curve from 0 to pi has a value of 2 square units.
Exactly.
Exactly. This is
So for
exact.
The ones that we use the area, we could have used this formula.
Right, well, we don't know how to, we don't have a formula to find the area under a sine
Yeah,
curve.
but like we could use this same.
This is exactly what we want to use now.
for everything. No more area.
Well, there's some area. There's some cases, like
Like the
semicircles, we can't use this method because if, anytime you have a composition of functions, you would have to use a method that we haven't learned yet. So that's why I said there are no composition here yet. Everything's going to be just the formula. Well, you'll see, you'll see. Okay, well, how about 3x squared? What's that look like?
X cubed.
Okay, so it's going to be 3x to the third over 3, or just x cubed, evaluated from negative 1 to 2. So it's going to be 2 cubed minus negative 1 cubed. So we do the antiderivative, plug in the top number, plug in the bottom number, and subtract them. So we get, what? 8 minus negative 1. So 9. Again, what does this represent? This represents the area under the parabola 3x squared from negative 1 to 2 has an area of 9 square units. Okay, so far? Isn't this fun? It's kind of nice. It's not too bad. All right, how about this one? I think we had one like that on the worksheet.
1 over F.
Yeah, because we would end up with a negative x to the negative 1 over negative 1. So that would really just make it 1 over x. Right, the negative signs would cancel. Right, if you add 1 and divide by that. So what do we have? 1/2 minus 1. So negative 1/2. How about the next one? Secant squared. Remember, if you have trouble, just think what gives us a derivative.
You can have negative value.
Yeah, what does that, oh, just real quickly, if we end up with a negative value, it doesn't mean, right, it doesn't necessarily mean the whole curve is below the x-axis, but more of it is below the x-axis than above. That's okay.
Sounds good.
And what did we say? Yeah, but think, what derivative will give us secant squared? Tangent. Remember, you can always kind of look at, take the derivative of this to check your answer, because whatever the derivative of this is your integrand. Same thing here. I could check this answer by doing the derivative, and I should get back the integrand. Okay? And this is going to get evaluated from 0 to pi over 4. So we have tan of pi over 4 minus tan of 0. What do we have for tangent of pi over 4?
Root 2 over 2.
Try again.
Oh, wait, whoops. Oh, right, pi over, why am I thinking?
You're thinking sine or cosine.
Whoops.
I'm
I
guessing
didn't
that's
check
what you're
that, yeah.
thinking.
Are you actually,
Was that what you were thinking?
yeah.
I don't know. I know.
Math teacher?
My daughter thinks I am.
So now you're a psychologist.
She used to call me, I used to say I was psychic, and she interpreted as sidekick.
Oh.
She's like, this is because you're sidekick. I'm like, yes, I am your sidekick. Okay.
Madeline.
Average or mean value. Okay, be careful about this. This is not the mean value theorem. Okay? This, I know, there's going to be a lot of definitions. When we have time, when we're finished with the curriculum, we're going to go back and review like definitions and names of theorems, because you do need to recognize them on the AP. Like, they're not going to necessarily tell you the formula. They're just going to say, oh, find the average value. Okay? So average value, this one's important. Average or mean value.
You should create just one giant calculator program with every formula.
I'm sure there might be one out there. I just haven't looked. So first of all, here's a word that Microsoft Word doesn't recognize, but it is integral, right? Means that you can integrate it. So in order to integrate, it has to be continuous, okay? So it's on a closed interval. So the average value on that interval is going to be 1 over b minus a, and then the integral of f of x from a to b.
Okay.
So it makes sense? Does it make sense? No.
Absolutely.
No.
Are we supposed to prove
No,
this,
I
or
don't
should we just
think
take it on faith?
Take it on the paper.
What's the f of x dx, like times the derivative?
You don't remember it.
No, the integral.
No.
Oh.
Okay. Let me give you an example. I can show you. Remember, before we go through this, remember in the very beginning of the chapter, we started with the train problem, right? And we said, okay, train is going 75 miles per hour, I think it was, from 7 to 9. So what did we first figure out? We figured out that the area under the curve gave us the total distance traveled. Well, what would happen if we divided the total distance traveled by the time interval?
The average.
You would get the average speed. Well, of course, if it's constant, it's going to give us the same result, right? 150 divided by 2 hours
35.
would give us 75. So why is this definition useful? Remember, the next one we looked at is when it wasn't constant. So imagine if we had the formula for this function, this velocity function. The integral would give us the total distance traveled, and then divide that by the time interval, and that would give me my average speed or average velocity throughout. That's why we have that formula. Okay? Did that maybe click with some people? Okay. We actually did this a little bit already, so I'm just giving it the formal definition. So now we want to look at the next example. So find the average value, and just a little note here, the average value is a y value. Okay. So I want to find the average value of 4 minus x squared from 0 to 3. So you don't have to necessarily graph this, but what does 4x squared or 4 minus x squared look like? It's
This
here, right? No, it's just upside down parabola. Upside down parabola. It's not underneath the square root. And we want to just look at from 0 to 3.
I should stop watching this one to 1 o'clock in the morning.
Okay, so something like here's 3. So we're looking at, here our function goes from 0 to 3. what is the average y value over that time interval? Okay, so how are we going to find that? Well, we're going to find the integral, the area under the curve, and then we're going to divide by the integral, and that will give us our average y value. So we want 1 over, so remember here's our a and b, so that's going to go 3 minus 0. Then we want to evaluate the integral from 0 to 3 of 4 minus x squared dx. Remember the integral sign and the dx just tell us that we're taking the integral with respect to x. So the way that that's important, you see how we have just the constant 4? Because that says dx, I end up with 4x. If this said dy, then we would have 4y. Okay. It just tells us what variable to attach to the constant in this case. Okay, so what do we have? 1/3. We end up with a 4x minus x cubed over 3. Evaluated from 0 to 3.
That's the answer.
Well, we have to evaluate it. Okay, now the 1/3 out in front, you can, well, the nice thing is in this case, the lower bound, what happens when you plug in the lower bound? You just get 0. So you really have to just worry about plugging in the upper bound.
So if we, let's say the 0 was like a 1.
We would have to plug it in. So
But-
here's, I'll write it out so just so you could see it. So it's going to look like this. It's going to be 4 times 3 minus 3 cubed over 3. And then minus 4 times 0 minus 0 cubed over 3. So plug in the 3, plug in the 0, subtract them, then multiply that by 1/3. If you want, you could distribute the 1/3, but I usually think it's easier to evaluate it and then just multiply by 1 over 3. Matthew?
And if we get the x3 over
Add 1 to the exponent, divide by that exponent. So really I use the power rule for both. Think of the, whenever you have a constant, think of it as a 4x to the 0. And then you could still do the power rule where you add 1 and then divide by that. Remember, how would you check your answer? Take the derivative of this and see if you get our integrand. The derivative of 4x would give us 4. Would the derivative of x to the 3rd over 3 give us x squared? Yeah, you'd move the 3 to the front, subtract.
Is the bracket notation around the antiderivative indicating like the increase or the area under it?
This represents the area under it.
Okay.
Okay, what do we get? I have no idea.
1.
What do we?
1.
1. Sounds great. That sounds right. Because if you look at your values, it goes from 4 to what, -5, so the average value. Okay, so now we're going to take that definition of mean or average value and say that basically if it's continuous on the curve, so there has to be some average value and we can figure out where that occurs. So like that previous problem, we figured out the average y value, but we could also figure out the x value where that would occur. That's that. If we know the average y value was 1, what would we do to figure out x? Plug it, set it equal to? Remember, this is a y value.
Oh, yeah.
Set f of x equals
Set f of x equal to the 1 and solve for x. And then just make sure that your answer would be in the interval that's provided.
And if not, you say,
We did the same thing for mean value theorem when we did derivatives, right? We found the derivative, set that equal to f of b minus f of a all over b minus a, and then we figured out where that would occur. Does that sound familiar? So this is the same idea, but with antiderivatives. Oh, that was it. That was it? Wait,
Yeah.
did I have you continue?
Hopefully not.
Oh, that's too easy.
No, it's not. It's great. It's a great weekend.
I feel like we should continue.